Yeah. We were defining, just want to remind you of O. So we have definition A is a subset of R to the omega, right? So these are just the functions from, right? And then yeah, so we say and P is in all omega R. So these are finite functions from natural numbers onto the reals. Okay, so we say A is comega, weakly comega P. If this we already did, I'm just reminding you, if there exists a club such that for every sigma in C, the range of C T is contained in sigma, and A intersection sigma to omega section MP is comega in MP. The remark that we should keep in mind is that so sigma is countable, is of course countable, right?
Gregor, sorry.
Yeah. Yes. By the way, are we recording now?
Okay.
Recording?
Yeah, all good.
Yes, you are recording. I am also recording.
Okay. So take a sigma in there. Sigma is countable, right? But more importantly, when you look at sigma to the omega, most of those will be generic enumerations, right? So the set of G from omega to sigma such that G is generic enumeration, or is comega in sigma to the omega. So most thing you pick will be generic. They will be right, because you will be intersecting dense open sets. So okay, so just like we were doing with so last time, what did we do last time? We had the ultrafilter, right? So we had the ideal basically. Let I be the ideal. The other thing that you have to remember, we had a break, so I don't know what you guys remember and what you don't remember. So we had a super compactness measure on P omega 1 of R, right? And so if you remember from last time, I did two examples. One was we had any ultrafilter on some cardinal, and that induced an ideal on reals. Now we have a ultrafilter on P omega 1 of R that's going to induce an ideal on R to the omega. So let I be basically the ideal of so the ideal of sets which are not, right? So I is the ideal of A is not weakly omega for any P, basically. Right? So this is the ideal that we are forcing with. And then we, so that's this is part of the remark, or let me put one more. So in this case, we argue. Okay, that's how the notes are written, but that's basically what we are doing. We argue that the generic embedding given by I.
Well, what do you mean by this case?
Hmm?
What do you mean by this case? In case I is
In this case, in the last, if you remember from last time, I started introducing the after filter without saying what the ideal was.
Mhm.
And there is an ideal. So it's very similar to the previous case. In the previous case, last time I had two examples. One was we had an ultra filter on a cardinal that induced an ideal on reals, and then we showed that the ideal was precipitous in that the generic ultra power agreed with the embedding restricted to ordinals agreed with the embedding given by the ultra filter. Here it's the same thing. This is the ideal, and the generic embedding given by the ideal, given by I, restricted to ordinals, is the same as the embedding given by embedding given by the ultra filter minus regressive confidence measure. Okay. On a supermass measure on p omega 1 over. And so another remark, which is part of recall. So we let if G is generic over V, right? Then UG, which was the set of A is weakly omega. So this is the set of. So this is the generic ultra filter, such that A for some P, yeah. So there exists P in G. P is sorry, A is weakly omega below E is generic ultra filter. So that was the ultra filter. Okay, so what we want to show. So today we will show that the ultra power by this embedding is equivalent to the other one, to whatever I put in the remark, right? So that would be sort of the main things to show. We already covered that. Yeah, so I'm following Obra's notes. Here's a notation in these notes. But if sigma is from R to the omega, then image sigma is basically the set of sigma I omega, right? So it's the set associated to sigma. And what is, let me just make sure I have the pi correctly. Well, so pi. This is pi. So so this is pi. This is the pi, the embedding that will generate the reduction of UG onto mu, right? So what do we have? We already done that. So we proved Wash's theorem last time again. So last time Wash's theorem for UG, right? So this means the alt VUG satisfies phi f0 if and only if the set of sigma V satisfies phi. P. Okay. So we did this last time, and what we have not shown is that the autocars were founded, right? So we want to see today. We show that RPG is well founded. VG is well founded. Okay. So here's a theorem. We let A from out E mu into out V mu G be given by A of F mu, right? So remember, okay, let me write it and then I will explain. So things here are represented by functions from mu. Mu is the super compactness measure, right? Mu is the super compactness measure on, mu is a subset of that. Okay, so the space of mu is p omega 1 over r, so that means you have to look at functions from p omega 1 over r onto v, right? And then, so this can be our functions. And here the functions are, the base set is r to the omega as countable sequence. Here, it's the countable sets of reals. Here, it's the countable sequences of the reals. So we have to map. The natural map is f o pi, right? So pi will tell me the image of the enumeration of the set. F will act on the image. So define like that is elementary. And A word is identity. Okay, so that's what will show well-foundedness. this. Okay, so what does this boil down to? I mean, the elementary part, it's just Walsh's theorem. So this is the mark, and that is elementary. Follows from Walsh. Right, so we leave it as homework. Okay, so we need to show the other one. What does it mean that we want to show this? It means that I have some function on countable sequences of reals. I want to find an equivalent function, right, on countable sets of reals. That's going to be the key. So we have sort of the goal. We have sort of a function f from r to the omega into ordinals. We want to find h from the omega 1 of r, so uncountable sets of ordinals, such that what is h? Let me put h here because then it will not be will be less confusing, right? So h is what we're looking for. Okay, so what is h going to do? Well, it's going to agree with f, but they're on different spaces, but they're going to agree only when we compose with pi. Okay, but what does it mean to agree? Well, agree on a big enough set, right? Such that the set of sigma in R omega, such that f of sigma is the same as HO pi sigma. This is large. This is in UG, right? So if you have then what would this say? This would say that H in mu, right? So this would say this implies that H mu is equal to F UG. This is the hard thing. And okay, what is it that we're trying to do? You know that the function is defined on countable sequences. You want to somehow transform that into countable set, right? So I give you the set. Every enumeration has a value, ordinal value. You want to say that, okay, now I can pick one. And what is it that you're going to use? We are in the universe where the ideal of mega sets is as additive as you want. So we are going to use the pair property, right? Okay, so I have a countable set. Any enumeration has an ordinal value, but now I'm looking for one, right? One of these enumerations, such that that ordinal value is reached by omega many of the enumerations, right? So we want, so repeat is the idea. For each given sigma in the omega 1 of r, we have that each function, each x from omega to sigma has an ordinal value f x, right? Now, can we fix one on a large set? The answer is yes, right? Okay, so now we want to fix one such value. Okay, so now what do? We look at so for each alpha, that let's say D or E alpha be instead of all enumerations, right? All are in R omega such that the image of R is in such that the image of R is equal to sigma, and f of R is equal to R. Such that R is an enumeration, it gives you the value of. Okay, now one of these has to be comeager on a condition, right? So we have that for some condition Q. No, we have that for some alpha. E alpha is going to be E alpha is not meager. We cannot actually go to comeager. It's not meager on sigma to the omega in sigma to the omega. I haven't fixed anything yet, sigma to the omega, but then it means now I can find a condition in sigma for which it's comeager. Okay, so now let H alpha be. Sorry, let H sigma be.
Excuse me.
Yes.
Can you repeat? Like, what consequence of AD are we using here? So you said
that the union of meager sets means bare properly, really. That the arbitrary well-ordered union of meager sets is meager. Right? So let me write it actually.
Yes, please.
If you're not used to that, you should write it. AD, well-ordered union of meager sets basically the ideal of meager sets is infinitely by infinite, I mean, it's as complete as you wish. That's very convenient. This is one thing you don't have on the ZFC in ZFC, right? There's no ideal in ZFC that is as complete as you wish.
And what is the idea of proof of this fact?
Oh, it's just a bare property.
It's just
From bare property. Bare property implies this, because you could look at the well-ordered, the well-ordering of the reals, right? Bare property implies if is consists of meager sets then union A alpha is also meager. And for that you just need to look at the relation x is less than y if
Is this one that is like this one of these Koratowski-Ulam things where you use the product
Yes, yeah, you have to turn this into x less than y if x appears earlier than y, and then look at the sections of that, right? So
yeah.
Right, something like that. We can do next time if you're interested, but this is the classic part. And
It's
it's
like,
not
it's like similar to that the well order of the reals is not measurable using Fubini, right? Something like this you can do.
can you say again?
If you have like a well of the reals, you can use Fubini to show that it's ever, I
Yes.
think. And this proof is somewhat similar, if I remember correctly. Like
It's very similar.
okay.
You can right? I mean, you could look at the least such a sequence. So that means we can assume that my alpha plus one has has something new in it than the union of the previous one. Otherwise, the union of the previous ones is violating this. Okay, so each set, each A alpha is on the sequence for like we don't have repetitions, right? So we are in the minimal count, and then okay, so then it makes sense to say x is less than y if x appears earlier than y. Yeah, but what do we know for each y, right? So if you look at the relation, consider.
So okay, and then if you count in one dimension, you get a complete, and if you count in the you integrate in the other direction, you get a meter set.
Yes, x is in A alpha. I mean, what I'm saying is that we can assume that these things are increasing, right?
Well,
So here is first. So without loss of generality. So first minimize eta and assume that A alpha is roughly subset of beta for alpha less than beta. So I can do this if you're just taking the unions. Take your sequence and now for each alpha redefine A alpha to be the union up to including alpha.
Yes, sure.
Right? If the next, yeah, okay, good. All right, so now we say x is less than or equal to y. Well, let's put star here so that people don't confuse with the real one. If x is in A alpha and y, so for x, y in the union of A alpha, y is not in A alpha, and then for every y in the union of A alpha, the set of x is less than or equal to y is meager, but union A alpha is comeager, is not meager. And then you say, okay, well, if it's not meager, then it's comeager on something by bare, and then you get a contradiction. Yeah. So finish it. Finish as homework.
Okay.
Right. Okay, so this is like extremely useful thing because you have under AD you have a measure which is forever complete. Yeah, very, very, very convenient. That's why people say, and I hear this often actually. Okay, they say, "Oh, Grigor, you don't like axiom of choice." You work with AD, actually, you have more tools. What do you have under axiom? I mean, okay, maybe some people do have stuff, but you know, like this is an incredible tool. And the only other time you would have this is under Martin's axiom when and your kappa is less than what 2 to the omega. So anyway, you have way more structure, way more stuff under an axiom of determinacy than if you just assume axiom of choice. Okay, so where was I? Right. Okay, so we have that for some alpha, E alpha is not omega on sigma to the omega. But then what? Okay, so I'm going to say define H sigma to me, the least alpha for which it's not meager, right? Okay, so now continuing, define H sigma to be the least alpha such that E alpha is not meagest. Okay, so I'm outlining. This is not really a proof yet, right? But now what happens if you turn this into a proof? What are we supposed to do? So we're trying to prove some set is in UG, right? Look, we're trying to prove that I have an F, then I can find some H for which this set is in UG. But that's forcing, right? So what we're trying to prove is that certain set is dense, right? That set of conditions for which I have an H with that property is dense below, is dense. That's all. Okay, so there is some condition P around. Okay, but being in UG, that means I'm looking for things that are weakly comeager, which means I want now to have the set of sigmas for which I've defined this H sigma to be weakly comeager, yeah, or with some condition. So weakly comeager is always below some condition. Where is this condition going to come from? Well, if this is not meager, by bare property, it's comeager on some space. So there's some condition which turns this set into comeager, and that's where we use the supercompactness measure, right? So for given a sigma, look at all the conditions below which the set is comeager, and then you can fix one condition like that. Okay, so that's the proof. So now using supercompactness measure, we can find Q in sigma, no, Q in all omega R such that image of Q is subset of sigma, and the set of sigma such that H sigma is defined, right? H sigma is equal to F. There's another thing, right? So I'm defining H sigma to be the least alpha such that the alpha is not meager. That means for non-meager enumerations of sigma, you get the value alpha, right? So this is really going to be F of I want to say this is not what I want to say, right? We can find Q such that the set of sigma which are already enumerated, right? So which are sequences with the property that H image sigma, so the set given by sigma has the same value as F of sigma, is weakly comeager below Q. So why is that? Well, H sigma, for each sigma is a set of reals. We have this alpha for which non-meager many enumerations give me the same value, right? So if I have one of those sigmas, then I know that this equation is true for non-meager many enumerations. Okay, for each these type of sigmas, I have a condition that turns that set into a comeager set below it. But now conditions change. For each sigma, I have some condition in it with those properties. Okay, but now if you use supercompactness, you'll fix the condition. So that's how you get them. Now there are two things to do here. Either I leave this to you as a homework and you complete it, or I write it down more clearly. What do you want? Anyone?
Maybe let us write down a bit at least.
Oh, now? Okay. So proof of the theorem. Okay, so what do? We say, okay, we want, let's go back. We want to see, so fix a function and we want to find, right? So let f be a function from r to the omega into the ordinals. And we want to see that there is an h from p omega 1 of r into the ordinals such that the set of sigma in r to the omega with the property that f sigma is equal to h of the image of sigma, so enumeration of sigma is in UG. Okay, so that means I need to, this is a genericity, so that means I have to show that the set of conditions with this property is dense, right? So let D be the set of conditions in for omega r such that there is a function h, there is a function h into ordinals with the property that the set of such that the set of sigma such that f of sigma is equal to h of image sigma. Right now, I mean, the quantifier here is important. The set of for this p, there is such a function, right? Is weakly omega below p, is dense open in for omega r, right? If we show that set of conditions p for which there is a function blah 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 such that that set is weakly omega below p, then one such p will get into a G, and therefore the corresponding set will be of measure 1, right? In other words, what's written here is equivalent to what's written down there. Okay, so we fix a condition, right? So fix the in of omega r, and we want to find q below p in right. We want to find q in the class such that 1 for q is below p, and 2 there is an h from p omega 1 of r onto the ordinals with the property that the set of sigma in r to the omega f sigma equals h image sigma is weakly omega below q. Okay, so we work below P now, right? So we work below P. Let given sigma in P omega 1 over R, such that image of P, the range of P is subset of sigma. Let set H H sigma equals the least alpha such that the set of R in R to the omega with the property that they are, and it's an enumeration of sigma, right? With and f and that R is alpha, right? So I'm looking at the set of reals, a set of sequences that enumerate sigma and give me the value alpha is not meager in so I'm working below P, that means I have to look sigma intersection in P. Okay. All right, so now we do we do the trick that I was explaining. It's not meager.
You mean here sigma to omega,
Sigma to
like
the omega.
this Baire space.
Yes. Okay. So for each sigma, by super compactness of mu, right? Remember, mu is super compactness measure, so the set of sigma with this property is measure 1. Maybe I record that because mu is fine. The set of sigma in P omega 1 of R with the property that the image of P is contained in sigma belongs to mu. Right? So then I have measure 1 many sigma for which this H sigma is defined. Okay, but by Baire property, so by BP, for each, let's call this set, I give a set name. What should I call it? S. For each sigma in S, that is 2 in sigma, such that the set of R, right? Now I'm going to apply it exactly to this least alpha. The set of R such that image of R is sigma and f of the Q in sigma, f of R equals alpha equals I want to say equals H sigma. Not alpha. There's no alpha anymore. H sigma. Right? So I'm picking sigma in S and I look at H sigma. I know that non-mega many R's will give me the desired value, the value that I assign to sigma. Okay, so I want to say there is a Q for which this set is comega below comega in sigma to the omega intersection and Q. Okay, okay, but now by supercompactness, by normality, right? So by normality, we have Q in collapse omega r such that the set of so that it works for all measure one many sigma, yeah? The set of sigma in P omega 1 of r for each, let's call this guy as a name. Let's say A sigma. Right? Set of sigma such that A sigma is omega on and Q belongs to mu. Okay, but now just rewind everything. Because we want to say weakly omega below Q, right? So that would what that means. Once you have a measure one set in mu measure one set, you can translate that the set of enumerations is weakly omega, right? So what this is saying is basically so the set of enumerations of such sigma right? Such that A image sigma is co-omega on sigma to the omega, image sigma to the omega in maybe I should just go jump into the conclusion immediately. Right, so let's skip the step, right? So now if I look at the set of enumerations, I know that the A sigma is omega when I look at the image. What does it mean? That means this set, right? So if I look at the set of enumerations such that f of r equals h sigma, so that means f of sigma is the enumeration now, so sigma is this r now, equals h of image sigma is weakly co-omega below this. Oh, I forgot to say I made a mistake here. Well, no, I just forgot to say that Q extends NP, right? Because all I have is that the set is not meager on NP, so I can continue P such that Q is below P, right? So I can continue P to end up in the omega part. Weakly omega below Q. Okay, so this means Q is less than P and Q is in my P. And that's the end. Okay, so this implies that the ultra power is well founded, and not only well founded, but it extends the ultra power given by the embedding. So I don't know how much set theoretic background you have. This is very unusual. You have an ideal. I mean, let's see. So you have an ideal such that the generic embedding agrees is in V, right? You don't have to force to get. Usually when you have an ideal, you force with it, it gives you generic embedding. Okay, but that generic embedding restricted to V is not in V. Usually, generic embedding restricted to anything is, I mean, okay, restricted to ordinals is not in V usually. How do we get from embeddings with this property? We usually collapse a large cardinal. For example, if you collapse a measurable to become omega 1, and then derive do the argument that the trace of measure is the precipitous ideal, right? Then you can prove that the generic embedding agrees with the ultra power embedding. which you already had before. And here we're not collapsing anything, we're just forcing with col omega. I mean, we are collapsing it, we're collapsing reals, not a large cardinal. So we're collapsing reals, which is a tiny thingy, and we're getting as if you collapsed the large cardinal, right? So there's so that sounds like saying that under ADR plus theta regular, theta looks kind of like a large cardinal, because when you collapse it symmetrically to become omega 1, this collapsing omega to reals to omega will collapse theta to omega 1. Theta will become omega 1. Just like when you do Levy collapse of a measurable becomes omega 1. And then you have an ideal on omega 1. So here is the same situation. We have an ideal, we have this generic embedding, and it agrees with the thing we want. Okay. So it's this sort of stuff. What was the purpose of that monologue? It's a very unusual thing. You usually get this kind of stuff by collapsing a large cardinal. Okay, so what should I do next? I think it's probably better to work towards showing that the image of omega 1 is actually equal to theta. So next important step is, right, so remember our goal is to show that in the forcing extension, just recall our goal. If V satisfies V equals L of our set of reals plus ADR plus theta is regular, then V collapse omega 1 R. Right, so this is forcing. I think I misspoke. What I meant is that forcing with this, you get an ideal on which the generic embedding code is already in V. And then we're going to add, so we're going to do the star iteration. 1 omega 1, right? So this is going to force CH plus there is an omega 1 times ideal on omega 1. Right, so this is our goal. For this, there is an important step in this proof, which is to show that because now we know that the generic embedding, when we collapse the reals, is oh, okay. So why am I keep talking about that ultrafilter? That's the ideal. Remember, I'm collapsing. So look, the first one is going to collapse the reals to omega 1, right? At the beginning of this lecture, I said that this is the ideal. Well, that's the ideal that eventually will become our dense ideal, right? And we get the generic embedding by forcing with col omega R. Col omega R induces an ultrafilter on this ideal, and that's our generic embedding. So that's the ideal that's going to end up being dense. Now, there's a key step in this proof to show that the omega 1 in that generic ultra power, when you do it, it will go to theta. So we have to prove this key step. Then I have to remember why it's a key step, but that's besides the point. It's a key step. Key step in this proof is to show that phi mu omega 1 is equal to theta. equivalently, right? This equivalently shows that pi UG, UG being the ultrafilter induced from, right? Because we already showed the degree on ordinals equals to theta. Okay. So let's try to do this, yeah? Right, so I have to try to remember the proof. Okay, so why is it not gonna go? Which one is easy? We have to show that pi mu omega 1 is less than or equal to theta, and theta is less than or equal to pi mu omega 1, of course. Okay, so one of this is not hard. They both are not hard, but one of them is even less harder than the other. So let's see, I think it's this one. No, it's this one. Yes, I think it's this one. So we show that one. We first show sorry, this one, because you want to do the contrapositive, right? So you want to do okay. So assume theta is strictly less than pi mu omega 1. So what does that mean? That means that there is a function that represents theta, right? So there is f from what to what? Mu is on power set omega 1, right? Countable subsets of reals. So it has to go from these two ordinals, right? I'm looking for the function that represents theta. It has to go to the ordinals, but because theta is below the image of omega 1, by Walsh's theorem, it should be less than omega 1, right? Such that f mu is equal to theta. Right? Yes. Is it okay? I should be writing ordinal here, or it should be ordinal function, but because it's going to represent something that's less than the image of omega 1, right? Remember, this is the I mu, the constant function. Oh, sorry, this is the constant function omega 1, where Cx is right. And so if you just apply Walsh's theorem, you'll get this. Okay, now what is the idea? The idea now is each of these functions is a set of reals, right? Which means I have a map from a set of reals onto theta. So now let's, okay, if given a function f h from p omega 1 of r into omega 1, we can code h by a set of reals. Which is the set of x in in R, where x will code, where x codes what? X codes a pair of reals x0 and x1, right? Like evens and odds. And x0 codes the countable set of reals sigma, and x1 codes f of, oh, sorry, h of sigma. Right? So if you give me a function like that, I can code it as a set of reals. Now each set of reals shows up somewhere, right? And so this f shows up somewhere. So that AF let alpha be the wage rank of AF. Which is less than theta. Remember, the soup of the wage hierarchy goes to theta, right? Okay, now what? So I have some set of reals which codes the function. Now, now what do we want to say? Mhm. So I suppose you want to say that if you have an ordinal below this function, below what this function represents, then it will be coded by a wage rank below. Mhm. Let's see. maybe this is not how, yeah, maybe this is how you want to do it, but then you want to do, right. So I see. Mhm. Yeah, so okay, so here's maybe we prove this and finish it. I think what we want to do next, this alpha is not that important, but maybe it is. It's not that important to be honest. Yeah, so you want to do, what you want to do it next is use some basic AD plus theory. So by APR theory, every set, every set of reals is Susnum or Cosus. Okay, so we're now going to take trees for this AH. And I think that should be enough. For convenience, let's take it for more sets of reals, right? So let T and S be trees projecting to the universal. Okay, well, let's just do it more carefully. Oops. So I'm going to set A to be my AF, right? So that A be by definition AF. So this is the set that goes A, and now let AN be sigma n theory of HC, a membership. You probably just need sigma 1 theory or sigma 1 2. So sigma n theory over this means this is the same as the sigma 1 n plus 1, I believe. Sigma 1, maybe sigma, yeah, theory of HC membership, right? And so what I'm trying to do is trying to create a universe which will be countable universe, which is projectively correct about A. And then I want to show, yeah.
I think in the last line you wanted to write something else, right? It's sigma and theory of HC, so it's I guess sigma 1 and plus 1 theory of omega or something, or
Well, no, see that's the same, right?
so how is
One
sigma?
thing
Because
that you're multiplying, saying there exists a real. So you're not saying there is a set, but you're saying there is a real.
okay.
So here the quantifiers range over reals, here quantifiers range of any set. That's just all. But you can also do the hierarchy that you meant. So now let T and be trees such that projection Tn is An and S and I guess I don't need it because I already have Tn's, so I don't need these guys. I don't need also trees that project on the complements because if my the Tn plus 1 will always call a tree that projects onto n the minus 1, right? If I want to have also a tree that projects on the complement of an, then I have to, then I can decode it from the tree that projects onto an plus 1, because the sigma n theory will be coded into sigma n plus 1 theory. Okay. Long story short, you want to now consider structures of the form. So we consider models of the form. Let's call them n sigma, well, Tn sigma. So that doesn't make sense. So I'm going to put this here. Okay, where sigma is as a countable set of reals. Now, why did I do this? So the first thing we can notice, the first claim, which I should leave as a homework. The set of sigma such that R intersection n sigma is sigma, the set of sigma in with this property belongs to me. Why is this true? Well, imagine it was false. So that means n sigma has more reals than sigma. Well, that means that new real, which is not in sigma, will be definable. But in n sigma, everything is definable from a member of sigma and that sequence, right? Okay, so because you have normality, you can always fix that member from which it's definable. And then show that it could be that it's the same thing that all. Okay. The next thing that is maybe a little bit trickier to see, but maybe like to do next time, is that so let's call this sigma. Now, if sigma belongs, no, sorry, B. If sigma belongs to B, then well, here's a couple of things. Then A for each n, an intersection sigma. This is true for all sigma, not just this particular sigma. An intersection sigma is actually in n sigma. So an intersection sigma is actually equal to the projection of Tn in n sigma. B. This is the key property. The HCA membership as computed in n sigma is elementary equivalent to HCA in A. So what is, how are you supposed to think of this? Because what is A as interpreted in sigma? So where HCA membership and sigma is basically HC and sigma, A intersection and sigma and membership. Right? And so the last,
You said basically, do you mean that the A predicate is not literally interpreted as A and sigma?
can you say it again?
Because I'm asking about the word basically, because you said that,
There's no, I said basically.
yeah,
Oh,
yeah.
this, I think of this structure as that's the predicate, yeah.
But then why do you say basically? Isn't it literally the case?
Well, it's just a notation I just invented, so.
Okay. In this sense, okay.
I don't think it's not proper to write like that.
No, but like, it makes sense to interpret a triple in another model, right?
Right.
Well, so it's a definable object with those parameters. So yeah, I was confused that maybe there is some subtlety about A.
No, there's no subtlety. I mean, it's all, if I set it up correctly, all of this is very easy to prove, right? You want to prove that, for example, sigma 1 fact is true, but that thing is coded inside one of the trees. So, for example, you want to prove this, you want to verify what Tarski condition, right? Okay, so there is an X for which blah, blah, blah. Okay, so there is that X means there is a real that codes that witness, right? But that's coded into the tree. The tree knows that there is this thing. So there is something in my projection with that property. And that's absolute, whether there is something in the projection in your local universe or whether there is something in the projection outside. So this is not hard to verify. Unless I said, I might have made a mistake in the setup, but I don't think so because I took the trees. It would have been nicer to take also trees for complements so that we don't constantly code them from the trees of the high. But anyway, I think it's okay. So the next key point, which is actually, the next key property. So we have few key properties. That's another claim. So you want to show that if sigma is in B, then F sigma is less than less than cardinality sigma plus, so less than theta, less than theta of n sigma. There's one key point here, which I'm not sure if you're following that. Sigma is a countable set of reals, and sigma does not satisfy choice, right? Because you will not be able to define well ordering of sigma from sigma. We can try to prove that, for example. Here's another homework. So that for measure 1 many sigma, for real almost all sigma and sigma satisfies not x. Right? So this means that from sigma you cannot define a well ordering of it. Okay, we can discuss all of these claims one by one next time because we don't have much time. But let me just write down. Then F sigma is theta and sigma. Why would this be true? Let's end with on this thought. Yeah. So why would this be true? Because of what A was coding. Remember what A was coding? Let's go back to A. Where is my A? This is AH and A was AF, right? So I fixed the function which is giving me theta, right? Okay, it doesn't matter what function you call that. For any function, this will be true. So if I apply it to AH, then I would get the equivalent theorem for that function. Okay, but what does AF code or AH? This the X is going to code two pairs, X0 and X1. X0 is going to enumerate something, and X1 is going to give me the code of H sigma. And sigma being the thing that X0 codes, right? So my real is going to code two pairs. The first real from the pair will code a countable set. The other one will code the value of H. Okay, so let's see what happens here now. if I collapse, but here is the proof, right? So let G collapse omega sigma be n sigma generic, right? Then A, then in nx n sigma G, which by the way satisfies choice, this satisfies ZFC, there is x in n, so then n sigma ZFC satisfies choice, right? And there is x in n sigma G intersection A such that x codes up there x0, x1, and x0 codes that same set sigma, and x1 codes f of sigma. F of sigma is accountable. Why is there such a thing? Well, because I'm projectively correct. It follows from here, right? This structure, the key property is true in all generic extensions. Right? That's a key property, but then I have key property for all. Okay, see, key property. Key property holds in all less than omega 1 of V generic extensions of n sigma. So if I take something which is what does this mean? Holds in all generic extensions of n sigma that are obtained by forcing with which belongs to n sigma up to omega 1 of it, right? That doesn't look like V. So omega 1 of V will be an inaccessible cardinal in this model. So if you take forcing in that portion, so that forcing is countable in V, then there it will be true. In that extension, it will be true. Okay, so how do I know that there is an X like this? Well, I am applying the key property in the forcing extension by G. That key property says there must be a real which codes that little sigma now, right? This is countable, this sigma now. In n sigma G, the sigma is countable. So there must be a real which codes it in the outer model, in this portion here. There is a real that codes it, and there is another real which codes the value of f of sigma. So there must be such a thing in n sigma GA. Okay, but now notice that this does not depend on the generic, right? So let alpha be f of sigma. We have that alpha is less than alpha is coded by a real. So alpha is less than omega 1 of n sigma G, right? Because why is alpha less than omega 1? Because it's coded by a real. But what is omega 1 of n sigma G? You collapsed everything. This is really just theta. So that's what it proves. Okay. Okay, so next time we will use to show that this tells you, this gives you a bound on where f sigma has to be. Basically, I can now find a larger set such that this theta n sigma is less than omega 1 of that. So idea, we then find the set C such that for measure 1 many sigma in P omega 1 of R, f of theta of n sigma is less than omega 1 of L C intersection sigma sigma. You can easily do this by coding everything that I described into a bigger set of reals. Yeah, so you can easily obtain this, and then so if so now this basically tells you that I think F couldn't represent data. Right. So this will show, this shows, this will show that F mu is less than data. Because that's another function, right? F is below this function. Okay. All right. So there's a lot of. It would be, guys. It would be nice. I mean, some of these are quite easy if you know the stuff. They're quite hard if you don't know the stuff. So it would be nice if you tell me to stress some of it, to not stress some of it. Yeah. Then it will be more efficient. Okay. So let's stop it here. Can we stop the recording? Did it stop? Do you